So you are all welcome. We commence the class immediately. Welcome. So let me share my slides so that we can start. Okay, so we are still looking at some theories on convergence of measurable functions. Last class, we looked at the general case, that's stage 4, the general case. So of what we mean by our convergence, or I mean the function to be Lebesgue integrable. So today we will be looking at some theory characterizing those steps, step 4 especially. And then after that, we now look at properties of some properties, um, of Lebesgue measurable functions. Okay, so that's what we want to cover today. So let me just give us some theory. Remember that last class, we gave an example of a Lebesgue measurable space, a measurable space, which is the L1 space, capital L1 space. So let's look at this theory, theorem. The following families of functions are dense in capital L1. Yeah, if you recall, we looked at this space, which is the space of Lebesgue measurable function, the L1 space, capital L1 space. Those families that are dense are as follows: the family of simple functions, number 2, the family of the step function. I'm sure you know these are the families of function we use in constructing a Lebesgue measurable function. The families of step functions. And lastly, number 3, the continuous functions of compact supports. Continuous functions of compact supports. Okay, I'm sure if you each you would have seen from previous classes. I'm sure you would have seen each of these families being used in constructing a Lebesgue measurable function. Okay, so we are going to actually look at the construction of the proof of this theory. Okay, so your proof is as follows. If you have that f is an integrable function, on Rn, of course, we can, without loss of generality, we can choose f to be real valued. F could be real valued. Okay. Uh, Now you recall that for real valued, we can actually approximate the real and imaginary parts independently. That's in case you even use the C. You recall last class where we used a function that is C valued. We're able to construct the real and the imaginary part, and we're able to show that both of them are Lebesgue measurable. And so if we use the real part, so we can, of course, break up the function into the left and right. We did this last class, which you have f plus minus f negative, okay? So this obviously is measurable because this is measurable, this measurable linear combination of measurable function is also measurable, where, of course, you already know the definition of F plus and F negative. Both of them are actually positive. I'm sure you know that because this maximum of 0, F plus is defined as uh, F plus is defined at maximum, okay, of F and 0, while F negative is actually the maximum of minus F and 0. So each of these is positive. So you now discover that our job now is to show that since each of these is positive, we just want to show that F itself is positive. Okay? And to do that, we've already proved something similar like this. Yeah, I think 2 classes before now, where we used a function, a sequence of function that is non-negative and also a simple function. And we were able to use that to get something like this, if you recall. Let me just write what we got. Just a matter of simple construction of the proof. So we're able to get f minus phi of k. Of course, this function is in capital L1. I'm sure you remember the norm. The norm actually is the norm of L1 norm. So are we able to show this goes to 0 as k? You know, this simple function approximating this. So as k goes to infinity. Okay? So you now discover that obviously this simple function is close to f. Simple function close to f. That's the meaning of this actually. This simple function approximates f. That's the meaning of that. Because if this goes to 0 as k goes to infinity, that means that the difference between this is less than epsilon. So they are close, very close to one another. Okay, so The second part of the proof is that, of course, you look at number one. The number one have to do with the step function. If you recall what we wrote in that, the step function, the simple, I said step function, the simple function. If you recall what we wrote in that theorem, we said that the following families of functions are dense. The first one is the simple function. The second one is the step function. The third one is the continuous functions that has compact support. So you discover that this one is done for the simple function. So the second one, which has to do with the step function, you can do that as follows. You see by, you can note from one, that's the simple function, by one, you know that all that we need to do is to approximate simple functions by step function. Simple functions by step functions. Okay? And of course, you recall that simple function is finite linear combination of characteristic functions. That was exactly what we had at the beginning of this section. That's the talking about the class of Lebesgue measurable function. So you have simple functions as linear combination of characteristic functions of sets of finite measure. So in that case, you discover that all we need to do is to show that if you have the set E to be a set, then the step function phi, let me give us a new slide to write all that I've said. So you see that we have to show that if E is such is a set, then there exists a step function. Maybe you call it psi, so that the characteristic function we talked about, the norm of that characteristic function, which is defined over this measurable set that has finite measure, okay? The difference between this and the step function, actually the norm, of course, you remember the space we are in L1 space. This norm is also small, so it's an approximation, okay, of the step function approximation of the characteristic function. Okay, so this is also small, so that you begin to have similar thing like we did. In other words, if you have that the measure of E, remember that when we talked about sets that are measurable, if you partition your measurable set with rectangle, or the sets of interest with rectangles, the measure of that finite union, J counting from 1 to M, of your RJ, these are the rectangles, okay, is also measurable, of course. So you can say less than epsilon, less than 2 epsilon, that's okay also. So in that case, you can now see that this is small as saying the norm of um, the characteristics function minus the step function. The norm in L1 is actually less than epsilon or 2 epsilon. So it's small, meaning that this also converges to this, as of course you know, as j goes to infinity, if you like. So that's yet another approximation. So let's this time around begin to look at some properties of measurable functions, just like we did in measurable sets. So let's look at some of the properties. Okay, so let me share a new slides, and then we'll look at that. Well, if you recall the measurable sets, we talked about invariance or translation invariance, if you recall. Okay, so the same thing we have here for measurable functions. So invariance property. Okay, so if f is a function defined on Rn, the translation of f, f by a vector, um, let's call the vector h, you translate f by vector h in this space, which is Rn. That translation can be actually expressed as follows. Let's call it fh, from f, and you translate by h. Let's call it fh, okay? And you define that translation as follows. Fh of x to be equal to, f of x is f of x. But when you now translate by a vector h, you can call it maybe x minus h. Okay? So we actually want to examine the basic aspect of translation of this integrable function. So what does this say? In terms of, can we, if f is integrable, is f translated by this quantity h is integrable? And if I do Lebesgue integral on both sides, are they equal? These are basic questions that I want to ask. And of course, we've already answered such questions, if you recall, when we are in measurable sets. And we discovered that all those answers were in the affirmative, if you recall. If a set is measurable and you decided to translate by an A, for example, we're able to show that E plus A is measurable. And not only that, we're able to show that the measure of set E plus A and the measure E, measure of the original set, is exactly the measure of its translation. Measure of E is actually equal to the measure of E translated by A. That's when we are dealing with sets. We answered all these questions and they were in the affirmative. Now, now that we are in function, can we have similar results? That's what we actually intend to resolve. So let me share a new slide so that we go back to look at f translated by h and see if we can impose Lebesgue integral, and we have the same thing. So now, if f is Lebesgue integrable function, if f is integrable, then you can actually see that FH, the translation, is also integrable. Okay? And as a matter of fact, you see that the translation, or the integration over Rn, okay, of course, Rn, of this translate, this f of x minus h, of course, integrate with respect to s, will also coincide with when you integrate f. Okay, so well, we can check, first of all, we can check the assertion when f is actually the characteristic function over E. Okay? Of course, this is measurable. We know that already. So the if since that XE is measurable, then you see that clearly you have that FH, which you can now write as XE translated by H. Okay? X over E translated by H. Okay? Where, of course, EH, this is a translation, set translation, is actually X plus H. X plus H. We've already dealt with this type of sets. The translation invariant. Okay? Of course, your X is coming from E. Okay? Now, from the analysis we already made concerning the measure of EH and the measure of E, these are set translates. And we know that the measure of EH, it will actually coincide with the measure of E. So the measure of E translate and E will be the same. Okay, we've already seen that. And not only that, as a result of linearity, now you discover that the integral we have as a result of linearity, which is the integral we already have in Rn of f x minus h with respect to x, that integral we have. Okay, as a result of linearity, this will hold. It will hold for all simple functions. For all simple functions, okay, of course, maybe you can say increases or monotone increases pointwise, okay, and AE, that's monotone increasing pointwise AE, okay, to F. I'm sure you know what that means. We discussed this in details. I think 2 previous classes. Okay, so that you can actually summarily write the following, that if you are in L1, the norm of FH translate will coincide with the norm of F. That is, the norm of FH translates will coincide with the norm of F. Okay? So, meaning that the identity we have, that identity holds. F of X coincide with F of X. So that's that for you, the translate of a function and the function itself. They are not only measurable, the measure is actually the same. Okay, there's a whole lot of examples that one can actually construct. Let's look at the following proposition. All these characterizations, you can look at continuity also, and there's a whole lot of that one can look at. Continuity in form of open set, closed sets, all of those that we looked at using in sets. That's measurable sets. You can also look at the analogs in functions. A lot of them hold, so in fact, we don't need to repeat all of those. If you read the material I give to you, so if you go through it, you discover that I'm sure you'll be able to understand that also. So let's look at the following proposition. If you have, suppose that you have a function from the family of L1, capital L1, then you can have the following conclusion. The norm of F translated by H minus the limit, which is F. Of course, the norm is in L1. This goes to 0 as the translate H itself goes to 0. Okay, so the proof is actually very simple. Of course, if you take note of the theory of the results we've been looking at above concerning integrable function, that will not be far away. In fact, you can actually see that for any epsilon greater than 0, we can find a function. We can find a function, call it g, okay, so that so that the norm of your f minus the function g you talked about is actually less than epsilon. You can approximate f by that g. Okay, so if I have that f translates minus f is written as gk minus g, okay, plus fh minus gh okay, minus f minus g. We are just writing this in this format. Okay, you can see gh minus gh plus gh minus gh is gone. Okay, you see that plus f minus f is gone. So all we have left is fh, which is this one, minus f, because minus g is plus g minus g is gone. Okay? So if you write this in this format, you simply see that the norm of fh minus gh is actually the same thing as the norm of f minus g. And of course, g approximate f. So this norm is less than epsilon. And of course, you know that g is continuous and it has a compass support. So in that sense, you can have the following. You can have that norm of GH, norm of GH minus G, okay, can be written as, of course, the norm in L1 or in RD is simply the integral in RD, okay, the absolute value of G. These actually represent the translate. So you will not forget that. So you are talking of gx translated by h, then minus g of x. Okay. And this, you are integrating this with respect to s. Obviously, you see that the whole of this will go to 0 as h goes to 0. As h goes to 0. Okay. Because this function is minus this plus this goes to 0 as h goes to 0. Okay? So if the modulus of h is less than delta, where delta is small, then you have that the norm of g h translates minus g is also small, is small. And of course, the same will now, as a result, you also have the same for f. fh translate minus f is less than epsilon whenever delta h is less than h. Whenever no norm of h, which is absolute value modulus of h, is less than delta. Okay, so all these are simple approximation of translates of a Lebesgue measurable function. Okay, so let's see further theories that has to do with further approximations of Lebesgue integrable functions. Right. I want to look at um, Okay, so I think the material that I gave to you, you can look at it. What is left there is you have all those theories there and some exercises. So that I think we've done a lot of justice to these type of functions that are integrable. So we want to generally look at differentiation and integration. That's the next thing that we want to look at in the spaces of measure. Okay, so okay, so that's the next section that we want to look at: differentiation and integration in general in spaces of measure. Okay. Differentiation. I'm going to give you exercise. I don't know if have you gotten the material that I sent before? I want to know those that I've gotten, so that I give you some practical examples. If you look at, to start with, have you gotten that material that I sent through Mr. Yomi?
I, I, I
Do we
didn't get
have,
any particular example.
you said
No,
you have it?
I don't have it. I mean, I just have some books, the books for lecture, but I didn't get the particular examples
You
you are
didn't get
talking
it.
about.
Okay, what you will do, send me an email to my email. Do you have my email? My
Mm.
email,
Uh,
my email. Just send me an email to any of the GAOKK1, that's number one, at yahoo.co.uk. Just send me email there, or this one, Godwin dot Godwin dot OKK at futo.edu.ng. Just send email to any of this. Once you send, then I will now reply by uploading attaching the textbook. Okay. So what you will now do in
yeah,
the
yes.
textbook, okay, so just look at that textbook that I will send. Look at page 95. Page 95, look at problem. There are problems. That's six problems. The problem in this page 95. Look at questions 1 to, I want you to 1 to 6 here. Question 1 to, no, 1 to 5. Question 1, 1 to 5. Problems in that page 95. Question 1 to 5. Problem there is problem 6. So numbers 1 to 5. Okay. So look at that and then see the ones you can solve. I hope you are still doing your tutorials with Daniel Francis.
No problem.
Okay.
Uh,
Okay.
I I think we didn't start the measure theory
Okay. Has not
because
started.
I don't know about the 2 weeks ago, but the last week I'm waiting
Uh,
for him in online, but he didn't.
Sure.
Okay.
Okay, I'll find out. I'll find out. It's okay. So, possibly he will also look at those exercises with you. Okay, so let's go to the next topic, which I want to look at: differentiation and integration. Differentiation and integration. Now, the differentiation and integration, these are inverse operations, which we already know from our reanalysis perspective. Of course, we want to re-examine this basic idea in the framework of the general theory that we've been studying in measure theory. Okay, you must understand that this measure theory is actually a generalization of R, what you did in reanalysis. Okay, in fact, remember that in reanalysis is just the real number system, which is this. So all the integration and differentiation you learned in calculus was based on this. And measure theory is an extended system, which you have R star. Instead of looking at R, we are looking at R star, which is actually R itself. This one, the set you already studied, union, these two objects, minus infinity, comma, plus infinity. So you now see that this is an extended system. Okay, so we want to re-examine this differentiation and integration, which you've already done here in R. We want to, now that we've looked at concepts in R star, that's measure theory, so we want to re-examine this same concept here. That's our intention actually. Okay, so I'm going to share a new slide. Now we examine the following problem. Examine the following problem. The following problem. Number one, suppose f is integrable on AB. I'm sure you know that. Usually in R, we look at, we integrate over closed and bounded interval. And capital F is the indefinite integral. Is the indefinite integral, that is capital F of x is equal to the integral from a to x of f of y with respect to y. Now, the problem now, does this imply that capital F, the indefinite integral, is differentiable? Is differentiable? And that if you do f prime, you will recover f, you know. These are things we already know in R. So Now, we actually see that the affirmative answer to this question depend on ideas that have broad application and are not limited to the one-dimensional situation. So we are going to see that as we proceed. Now, we look at the second question also. This we are just generating questions that, we look at as we progress. So let's look at the second question. Now, the second question, we reverse the order of differentiation and integration as follows. Number 2, we ask what conditions on a function capital F on AB close bounded guarantee that F prime of X exists. And when we say exists, we mean almost everywhere. Okay? This function is integrable and that, the FTC, fundamental theorem of calculus, holds. I'm sure you remember the fundamental theory of FB minus FA is actually the integral of from A to B of the derivative of f of x with respect to s. Okay, so those are the questions that we want to re-examine under the framework of what we already have studied. So let's begin with differentiation of the integral. Differentiation of the integral. So we start with the first problem. The study of differentiation of the integral. Okay, so if f is given on AB close bounded and also integrable, and integrable on that interval, this interval close bounded, we let capital F of x to be equal to integral from a to x of f of y with respect to y. Of course, you know that AB is close bounded and x varies from there. In other words, A is less than or equal to x, less than or equal to b, so close bounded. Now, to deal with the derivative of f, capital F, okay, which we write as f prime of x. Of course, you record the definition of this. If you record the definition of this, let me just write it out. If you recall, f of x plus h, that's the definition, minus f of x all over h, where h tends to 0. If you recall, this takes the form of as follows of 1 over h integral x up to x plus h f of y dy, which you can write as equal to 1 all over, just by notation, you can talk of modulus of I, okay, of integral, this time around over I, over I. This is a constant out, so 1 over modulus of I. I'm going to explain what that I is, okay, of f of y dy. Okay, I was actually used, this notation as x comma x plus h, okay. So, and of course, the modulus of I is the length of that interval, okay? Of course, you know this is an interval from x to x plus h. So you're looking at the length. That's the modulus of I, okay? So we make the following observation. By reformatting that integral we've written above, you make the following observation. If you take the limit as the length of I, that's the modulus of I, goes to 0. Okay, of course, you are picking x from the interval I, okay, of 1 over modulus of I, the integral over I of f of y dy. You discover that you are in f of x. Okay? You are in f of x. Now, if we assume that f is integrable on Rd,
Sorry. Is that capital
yes,
F of X?
you said?
Is that capital of F of X
This is
or
small
small
f,
f of X?
small f, not capital, right? You know, the capital has to do with the indefinite integral. This is small f, okay? Now, if you suppose that this f is Lebesgue integrable, that's integrable on Rd or Rn, and we ask the following question. if f is integrable on Rn, now is it true that this integral, that is, if you take the limit as let's define it in form of open sets, because this I is an open interval. So if I take limit as let's call B open interval, measure of B goes to 0. Okay, of course, X is from the interval now, which is we are using the ball, open ball. So X is from B. Okay, 1 over modulus of the interval. So 1 over the measure of B. Okay, measure of B. The integral over I over B now. Okay, of f of y dy. F of y dy. We say that is equal to f of x for AE. For AE. So we are asking questions. If you can, does it mean, if I take B now being an open ball, open ball, can we translate this to this? That's a question. We need to answer that. Actually, the answer, the answer is actually a problem that we will look at also. It's a lengthy one, but let's start looking at how we can resolve it. If we don't finish it today, by next class, we'll round it up. Now, first of all, we remark that if B is any ball, of radius r, of course, r is a real number from Rn, then the measure of B, of course, it has a finite measure. If you have, so you now have that the measure of B can be expressed as, for instance, maybe you call this VDR to power, the dimension can be n. Okay, the dimension, this V, let's call it Vn, is associated with the space. So Vn r to power n is a finite measure, where, of course, Vn, okay, is the measure of the unit ball, Okay. Well, the special case where f is continuous at x, the limit converge to f of x. We've already seen that previously. So in other words, given epsilon greater than 0, you can always find a delta also greater than 0, such that, that's continuity axiom, such that the modulus such that the modulus of f of x minus f of y is less than epsilon whenever you have that the modulus of x minus y is less than delta. Of course, since we have that f of x itself, f of x minus 1 over the measure of b, the integral over b, f of y dy, is actually the same thing as saying 1 over the measure of b, the integral over b of f of x minus f of y. We find that whenever b is a ball of radius, delta is positive, so delta over 2 is also positive, that contain f, then we can actually put modulus on both sides. In other words, you can actually write the following. That's putting a modulus on both sides of that. You can actually write that the modulus of f of x minus 1 over mb, okay, integral over b, f of y dy is less than or equal to 1 over the measure of b, integral over b, f of x, just simply putting modulus on both sides. That's what you're doing. Dy. This converges, okay, as required. So because of our time, likely another class will be holding very shortly. So, and it's already 8. It appears that some of you used to forget. I've been, to show up on time for our class. Our class usually is 6 to 8. So the next class on Saturday will be 1 to 3 on Saturday, while Tuesday class is 6 to 8. So please, let's show up on time. We have to leave the Zoom now for other classes that will be holding. So please, let's show up on time on Saturday. Saturdays is 1 to 3, while Tuesdays, like today, is 6 to 8. So it's already after 8, so we have to allow the Zoom for other classes. I want to find out if there's if there's a question, any question before we go.
A question for me, Prof. Thank you.
Okay. Okay, thank you very much.